Hi everyone, and welcome to the second of 4 videos going through some past exam questions on the topic of neutralisation, but also with some other acids and buffers questions thrown in there as well. So this first question is definitely a neutralisation question. We've got our titration curve here. We can see what's going on is that we've added sodium hydroxide from the burette to an acid. We've started off at a low pH, and then we've ended up with this characteristic kind of S-shaped curve where it's almost horizontal, where we're adding the alkali to the acid that's in excess, so it doesn't change the pH much. Then all of a sudden the pH changes very quickly, and then at this point you've basically got a solution of an alkali, so adding more of the alkali doesn't make much of a difference. So what's going on here? It wants us to write the equation for the reaction that takes place. Okay, so it's saying 1 mole of glycolic acid reacts with 1 mole of sodium hydroxide. So our glycolic acid, they've given us the formula here, so we're just going to copy that. HOCH2COH. It's going to react with sodium hydroxide, and we're just going to make the sodium salt of this, right? So we're going to with HOCH2COO minus Na plus and H2O. It's not too bad. Right, it then says determine the concentration of the sodium hydroxide. So we've got to do some sort of a calculation here. So what numbers have we got? They've given us numbers here. This is the volume and the concentration of the glycolic acid. So we're going to let's start with these two and calculate the moles. Okay. So we're going to do 25 over 1,000 to get that into decimeters cubed, times that by the concentration. So let's see what we're doing here. So 25 divided by 1,000 and then times that by 0.125. So we've got 3.125 times 10 to the minus 3 moles. And what was that? That was of the glycolic acid. Okay. And then we've just seen from the equation that we've written that 1 mole reacts with 1 mole. So it's a 1-to-1 ratio. So therefore we've got 3.125 times 10 to the minus 3 moles of sodium hydroxide. And then if we want the concentration, we're going to have to divide that by the volume. Where are we going to get the volume from? It hasn't told us the volume up here. The volume is going to come from this graph. Okay. The volume of sodium hydroxide that was needed to react is the volume that comes from the equivalence point, okay, from this vertical section of the graph. So we're going to measure this down here, okay, and this is going to be 22 centimeters cubed. Okay, so that is the volume of sodium hydroxide we've had to add in order for it to neutralize the acid. Okay. So that's what we're going to use in our calculation. We're going to do our 3.125 times 10 to the minus 3 moles divided by 22 over 1,000 decimeters cubed. Okay, so let's calculate that. We've already got our number here. Divide by 22 divided by 1,000. And we get 0.142 moles per decimeter cubed. Okay. Right, carrying on. Then says here that we want to carry out this titration using an indicator. What important factor does the student need to consider when deciding on the most suitable indicator to use? Okay. Well, what we need is the indicator to change colour at the right point. So the end point of the indicator, remember the end point is the pH at which the indicator changes colour. The end point of the indicator, when do we want it to change colour? Well, ideally we want it to change colour at 22 centimeters cubed, right? That's the point at which the neutralisation happened. But in practice, as long as it changes colour within this vertical section of the graph, we're okay. So it doesn't necessarily need to be at exactly pH 7. If our indicator changes colour at pH 9, actually we're still going to read off 22 centimeters cubed, okay, because we've got this vertical section. So it doesn't need to be perfect. You know, pH 10 is probably still going to be pretty much okay. So as long as it's within this vertical section, we're okay. So the end point of the indicator should match the vertical section on the pH titration curve. Okay, and remember, you can tell the end point of the indicator also if you give it pKa. So sometimes they might give you indicators and say it changes colour at pH 4.2, or they might say its pKa is 4.2, okay, and it works out as the same thing. Right, what have we got here? So we've got our glycolic acid. It wants us to then write the expression for the Ka for glycolic acid, okay? So Ka is going to be, what was the formula of the acid again? Let's bring it back. So here's our acid here. So it's going to be this on the bottom, HOCH2COOH. Okay. And so therefore it must be H plus and HOCH2COO minus. Right, it now wants us to calculate the Ka, okay? So glycolic acid is a weak acid, so therefore we're going to use the trick that we looked at in the previous video, where whenever you've got a weak acid, you can say that when the acid dissociates, it's going to produce one H plus ion and one of the negative ion. So these two concentrations are going to be equal to each other. So we can say that the Ka will be equal to H plus squared over this concentration. So therefore, it's going to be, how do we get the H plus concentration? The H plus concentration is going to be 10 to the minus pH. So it's going to be 10 to the minus 2.37 squared divided by the acid concentration is 0.125. Okay. So that should work out for us. So we're going to do 10 to the power of minus 2.37. So that's our H plus concentration. We're then going to square that, and then we're going to divide it by 0.125. And we get a value of 1.4, does it say how many decimal places to do it to? No, it doesn't. So I'm going to call that 1.46 times 10 to the minus 4. And what would be the units? Ka is always going to have the same units, okay, because we've got two concentrations on the top and one concentration on the bottom. So we're going to end up with units of moles per decimeter cubed. Okay, and that is always the units of Ka. Okay. Other equilibrium constants, if you've got Kc or Kp, the units will change. But for Ka, the units are always going to be moles per decimeter cubed, because you're always going to have the two concentrations and the one concentration on the bottom. Finally then, we've just got a 1 mark question here that says calculate the percentage molar dissociation. So for this then, what we want to do is say, well, how much of it has dissociated as a percentage of the total? Okay. Well, what represents the acid that has dissociated? Well, when the acid dissociates, it produces an H plus ion. Okay. So the percentage dissociation is going to be the H plus ion concentration as a percentage of the acid concentration, and obviously times it by 100. Okay. So it's going to be, we're going to have to go back and calculate this again. So it's, the H plus concentration was 10 to the minus 2.37, wasn't it? Divided by, the acid concentration was 0.125. And then times that by 100. And we've got what, 3.4%. Okay. So this very nicely shows that the glycolic acid is definitely a weak acid, right? It's not fully dissociating. It's nowhere near fully dissociating. It's actually a very small proportion of the molecules that actually dissociate. Okay, so that does seem like a very low answer, but it is reasonable. Okay, that is in the right sort of ballpark for a weak acid. Most weak acids are probably less than 10% dissociated, so that does seem reasonable.